All right, welcome back. Now we'll continue our discussion. Now this is where we've left off in our last video. So we have this illustrations for our one-way shear. Okay, so this distance is L over 2 plus C over 2 minus D. So what is L over 2? That's just 2.9 divided by 2 plus zero point 0.5 divided by 2. But we can now write our equation for the capacity. I mean the factored loads for one-way shear. Now we have V sub U is equal to the factored soil pressure times the area. So what is this area? Okay, so this area is just B times this distance. Okay, so B times L over 2 minus C over 2 minus D. Okay, so this is positive. Okay, so if you substitute the values, you get a 0.384, that's in megapascals. Then times the beam width, which is 2,900 in millimeter, times the, if you do the math here, if you substitute the values, then what you get is 1,200. Okay, 1,200 minus D. Okay, so that's the equation for our load side. Okay, and this one is in mm. Now for the resistance side, you can calculate that as phi VC is given by this equation, phi times 0.17 times the lambda times square root of fc prime times times b times d. Okay, so since this is in shear, then we have a value of reduction factor value of 0.75 times 0.17, and since we'll just assume it's a normal weight concrete, then that's going to be equal to 1, and our fc prime is 27.5 megapascals, and our b is 2,900, and this is our unknown, the d. Now if you equate this, the resistance side is equal to the load side. Now you equate these two equations. Okay, so you input that in the calculator and try to do the shift solve function. You'll be able to solve for the depth. So the depth is equal to 437.77. So our depth, that's our depth 1, is equal to 438 mm. Okay, so that's for our one-way shear. Okay, so next we'll check the two-way shear. So determining the footing thickness based on two-way shear. Okay, so first is to draw the footing, let's say the footing plan. Okay, so this is our column, and then we have this critical section at a distance d all over 2. Okay, so from this face of column to this portion, we have d over 2, and this one is also d all over 2, and this one is our 0.5. Okay, so this is our tributary area. Right. So now let's solve for the perimeter B naught at the critical section. Is just, since this is a square, then it's just 4 times C plus D. Okay, so we can further simplify that to maybe 4 times and express that in terms of millimeter. That's going to be 500 plus D. Okay, so now we can write the equation for the load side. Okay, so V sub U on the load side is equal to the factored soil pressure times the area concerned. So the area concerned is B squared minus C plus D squared. Okay, so what is this? Soil pressure, factored soil pressure, that's 0.38 0.384 megapascals times the 2900 mm squared minus 0.5, not 0.5, that should be 500 plus D, okay, squared. Okay, so that's our shear on the load side. And now if we solve for the shear capacity of concrete, then we have actually 3 conditions. So remember that we have 3 conditions, except that the ones probably governing in this problem is the third one. So we'll just use directly P 1/3 times the lambda. Okay, so we have the concrete modification factor times the square root of FC prime times the perimeter at the critical section times D. Okay, so since this is shear, this is the reduction factor is 0.75 times 1/3 times 1 times the square root of 27.5 megapascals times this where is it, this one, times the 4. Okay, so 4 times, okay, 500 plus D, okay, times, okay, D. Okay, now since you have the 2 equations, then if you equate that, VC is equal to the factored loads, then you'll be able to compute for another another step. Okay, so we have a D of that's 525.4. Okay, so 0.45. Okay, so meaning that the D would be the max of D1 and D2, which is equal to, okay, so what is our D1? Our D1 is 438. So we have 438, and then this one is 525.45. So meaning that this one governs. Okay, so therefore our D is 525 mm. Now let's solve for the moment capacity of the footing. To solve that, we have to first draw okay, so let's just write solving for the flexural capacity. Okay, so first let's draw the plan view, and then at the bottom of this is the elevation view. Okay, so this is our footing plan. It has a 2.9 meters on both sides since it's a square footing. Then this is our column, which is this is 0.5 meters. Now we said that the the flexural capacity, the critical section, is actually at the face of the column. So since this is a square footing, then it means that it, it will have just the same a critical section on both sides. Okay, so let's say this is our section, and we will have our shaded area something like this. Okay, so if this is 2.9 and then this is 0.5, then what would this distance be? Okay, so that's our x. Now if you do the math, it's just actually 2.9 minus this column width divided by 2. Okay, so that's just 2.9 minus 0.5 divided by 2, and that's 1.2 meters. Okay, so to draw the elevation view, so this one would be our critical section, and then below this, below the or underneath this shaded area, that's actually the area of the um, where the soil pressure is acting upon. Okay, so that's our factored soil pressure. And of course, since this is a rectangular, then the moment arm will be, or let's say the resultant of all the loadings within this area would be at the centroid of this rectangular area. Okay, so the distance from the centroid to the face, that's gonna be our x over 2. Okay, so now let's solve for. Okay, so solving now for our um, factored load, um, or let's say m sub u. Okay, so that's our factored load, which is just the factored soil pressure times. Okay, so this is the load, and then this is the load distribution. Then we have to multiply that to the area, which is, this is b, this is our b. Okay, so b times x, that's our area. B times x times the moment arm. Our moment arm is x over 2. Okay, so we can simplify this into b times x squared. So x times x, that's x squared all over 2. Now if we substitute the value, this is 0.384, that's in megapascals. And then, so take note, if you're using megapascals, then you have to use the appropriate units for the length. So that should be in millimeters. 2,900 millimeters times the x squared. So that's 1,200 squared divided by 2. Okay, so take note, if this is our unit, then our factored load will be in the unit of Newton millimeter. But typically when we're solving for moments, loads from moments, it's usually expressed in terms of kilonewton meter. So just like what we did in the calculations for singly reinforced beams, then we can just divide this um, by 1 million. Okay, so that's 1 times 10 to the 6 to convert this Newton mm okay, to kilonewton meter, then you have to divide it by uh, 1 times 10 to the 6. Okay, so this answer would be 801.792 kilonewton meters. Okay, so now since we have the factored load, then we can solve for the nominal capacity. Okay, so this is our equation, that the factored capacity is equal, or let's say greater than or equal to, the factored loads, and therefore our nominal capacity is just this factored load divided by the reduction factor. Now, we'll assume a reduction factor of 0.9, so meaning that it's in um, tension control. Okay, so 801.792, that's in kilonewton meter. So if we do the math, then we will have 890.88 kilonewton meter. Now, once we have this nominal moment capacity, then we can solve actually for the steel ratio. So recall that we have this equation in the topic of singly reinforced beams. We have this equation 0.85 Fc prime all over Fy times 1 minus square root of 1 minus 2 mn, that's our nominal moment capacity, divided by phi times 0.85 Fc prime times b, and then d squared. Okay, so this is our working equation for the steel ratio. In singly reinforced beams, we didn't actually use this in solving analysis problems. Okay, so this one comes into play when actually you're dealing with design problems. So meaning that we say design, then meaning you're given the loads, and then what should be the geometry uh, or the steel area. Now for our case, we have the geometry, but the steel area and how many number of bars we need to put in there, that's what we're actually trying to solve. So this is our working equation. Now if we substitute the value, but before that, I'd like um, to point out some um, important units that that we'll use here. So for our nominal moment capacity, we have solved that in terms of a kilonewton meter. But if we're going to use the megapascals in, let's say, Fc prime, and that's in megapascals, and Fy is also in megapascals, then this one should be in Newton millimeter. And take note, this one, the B should be in mm, and this D is should be in mm. So take note, that's D raised to 2, or D squared, so that's mm squared. Okay, and this square root sign goes all the way up to this D squared. Okay, so now if we do the math here, if we substitute all the values, then we'll obtain a steel ratio of 0.00359. So take note, for steel ratio, we need to have a value, or a decimal place. Let's say 1, 2, 3, 4, 5. So probably 4 or 5 decimal places. So that's typical for steel ratio. Now, by the way, then before I forget, this D value, if we solve this, it's actually um, if we draw the section. Now we said that we have reinforcements on both sides. So let's say this one is the bottom bar, and then this one would be the top bar. Okay, so the one that we've solved from shear is actually from the top face to the centroid of the top bar. Okay, so that's our D, and actually we solve for the one-way shear and two-way shear, and the maximum value that we got is the two-way shear. So that's our D here. Now, for the D that we'll use in this equation for the moment, for this steel ratio, we need to have this D. So from the top face to the actually to the to the outer face of the bottom steel. Okay, so that's our D. And from this surface, or let's say the surface of the bottom steel, the bottommost surface, to the bottom of the concrete, or to this bottom of this footing, that's our um, concrete cover, which is 0. No, that's 0. That's 75 mm. Okay, so we have this. We have a value of that's 526 millimeter, and we're also given that these bars are 25 mm diameter bar. So meaning, if this is 25 mm plus half of the 25 mm, so that's just simply 1.5. Okay, so 1.5 times the bar diameter. So that's D sub B. Okay, so therefore our D is D sub 2 plus 1.5 of the bar diameter. So if we substitute the values, we get 526 plus 1.5 times 25, and we have 563.5 millimeters. Okay, so that's our D. So meaning that our HC, or the height of the concrete footing, or let's say the thickness of concrete footing, that's gonna be the D plus the concrete cover. Now, if our D is 563.5 plus 75, then that's gonna be 638.5. Now, if we compare this H sub C to, um, let's say this is H sub C actual to the one that's assumed earlier, then we have actually it's less than our HC assumed. So therefore, it's okay. Now, if it's not less than, if the computed height of the footing is greater than the assumed footing height, then you have to redo the computations. Okay, so again, the the effective depth here that we'll use is the depth at the bottom face um, of this bottom steel. Okay, so now since we have the steel ratio, then meaning we can solve for the area of. Now recall that the area of steel, that's the steel ratio times B times D. Okay, so that's the width times the effective depth. Now the steel ratio is 0.00359 times our width, which is 2900 mm, and the depth of 563.5 mm. Okay, so if you do the math, what you get is 5,866.6 mm squared. Now, whenever we solve for the area of steel, then we have to check the minimum, or let's say required minimum area. Okay, so now let's check the minimum area AS mean, and recall that our minimum area is the maximum of the two conditions. So we, even though I didn't include this in this particular lecture handout, but this AS mean is just the same as the AS mean for singly reinforced beams. Okay, so uh, the first condition is just FC prime divided by 4 Fy times B times D. And another condition is 1.4 BD all over Fy. So this one is in megapascals, so this one should be in millimeters. Now if you do the math, we have these following values. Okay, we have 7,790 mm squared, and another one is 8,300 8,319.3 mm squared. Oh, so therefore the maximum of the two is 8,319.3 mm squared. So we see that AS mean is greater than the calculated area, which is which means that we shall use AS minimum. Okay, so now solving for the required number of bars, we can use this equation. N is equal to the AS. It's like the total steel area that's required in our section divided by the area of a single bar. And in this problem, that's 25 mm. That's the area of the 25 mm diameter bar. And this total area, it just so happened that this AS mean is greater than the calculated area, steel area. So that is why we'll use it here. So if we substitute, we get the value of 16.9 bars. Okay, so therefore we can just round it up. Let's say 17 bars. So meaning that if we draw it, then meaning we have 17 bars on this direction, and also we should have 17 bars on these directions. Okay, so we can just write something like 17 25 mm diameter bars, and since they're just since it's just square footing, then it's just the same 17